Okay, welcome to the final instalment of the NEAP 2021 Unit 3 and 4 exam. With me solving it, this is question 16. There are 5 questions to go. And I'm just going to show you question 16. I'm sure you've got it, but it has this particular diagram, which I've blown up to epic proportions here. And it says, Figure 16 shows the passage of a ray of green light, which I've drawn in blue, sorry about that, through various media. It passes from water into sapphire, and at a specific angle, theta, excuse me, the transmitted ray of green light only just reflects at the sapphire air boundary. Now, so that's water, that's sapphire, and that's air. Right? What you need to know is the 3 refractive indices. I'm just going to put this one away now. And basically the question is find theta. All right. So they said that it only just does this. What they're trying to tell you is that this angle here, that I'm going to call F, that one there, is the critical angle for sapphire. Right, so this is the sapphire, hang on. Sapphire. Because it only just reflects. Right? If that angle had been 1 degree smaller, right, it would have gone out. It would have refracted still, but it would have gone out into the air, right? But it didn't. So it nearly pretty much did that, right? And it's just reflected instead. So that's the critical angle for sapphire. All right, so you have to sort of reverse engineer this. You have to start here and work your way back. So at point B, we're just going to use Snell's law, of course. There's Snell's law, or there's most of Snell's law. We're going to use this twice. So at point B, that is the angle of incidence, and that's also F, right? Alternate angles. Excuse me. So they're equal. And the angle of refraction here is 90 degrees. So that's what I've got here. Angle of refraction is 90. Excuse me. Refractive index of the refracted side, the second side, is 1. Initial refractive index is 1.77. We've got to find that, and that'll be F. And then we're going to use it up here. So throw the numbers in, find F, find that there. That's 34.4 degrees. So that angle there is 34.4 degrees, and so is that one. So now you can go back to point A and do the same thing and figure out what this angle had to be. So now this is incidence and refraction for this point because the light is going there and there. So this is the refracted angle. So angle of refraction 34.4. Refractive index of the second part is 1.77. It was initial up here, it's final down here, it's refracted. Initial refractive index 1.33, find I, do the same thing again, I is 48.8 degrees. That's how to do that one. That's it's one of these questions that's reasonably easy to do once you figure out how to start. But it's one of those questions that quite a few people are never going to start. People are either going to get full marks or no marks for a question like this. Question 17. In a photographic electric effect, light is shone onto the metal cathode of a photocell as shown. Right? Light gets shone on there. Electrons leave. They hit the cathode. Sorry, they hit the anode. Pardon me. And they end up going around the circuit. All right. So the data is shown in table 1. The intensity and the photocurrent were qualitatively recorded. Okay. So light is shone into a metal cathode. Okay. Fair enough. So they changed the wavelengths. They had the same wavelength there, different one there, different one there, right? And they measured the intensity and they measured the stopping voltage. And also measured the photocurrent. It looks like they did that qualitatively as well. The only thing they've got a number for is the stopping voltage. All right, so it's a whole page of information. Now to the question. A, does any of the data above conflict with the wave model of light? Explain the answer. Okay. Best way to do this is to tabulate it. Right. You have to have the data and you have to have the wave model, right? So this is what I've got. I've got a table. This is the wave model prediction, and this is what the data showed. Okay. Make it as clear as possible that you're linking the two things that are mentioned in the question in your answer. Right? That's really good setting out. Okay, so the wave model tells you that any frequency of light will cause photoelectric effect to happen if it's intense enough. Right? And the reality, here's their data. Right? They had red light of a low intensity, nothing happened. Red light of a high intensity, nothing happened. Right? They had green light of a low intensity, the same as trial run, and something happened. So it wasn't happening because of the intensity of the light. Photoelectric effect didn't happen because of the intensity. This is less intense than that. So the intensity doesn't matter. Right? And low intensity, high intensity, same result. Low intensity, high intensity, same result. All right. So this is what you say. That's what the prediction is, and this is what really happened. Trials 1 and 2 were failures, but the other trials with the same intensities succeeded, right? These were successful even though they had the same intensities as this failure, right? So that proves that that can't possibly be right. Another one, stopping voltage. The wave model predicts that if you shine more light and more intense light, then you'll get electrons with higher maximum kinetic energy, and therefore you'll need a higher stopping voltage. That didn't happen. So this is the prediction, right? Stopping voltage is going to be higher with a higher intensity of light. The reality was, again, higher intensity of light. There's low intensity and there's higher intensity, same stopping voltage, right? So trials 3 and 4 had different intensities but the same stopping voltage. Same with 5 and 6, right? Trial 5 and trial 6. That is the easiest, quickest, clearest way to answer this question. Make a table, right? Here's the prediction, here's why it's wrong. Here's the prediction, here's why it's wrong. Spell it out really easily. Or you could try and fill half a page of lines with prose. And you might say the same thing twice, and you might run out of space, and you might not know how to phrase a sentence, right? Don't worry about the phrasing. That's what it needs, right? Keep it simple. All right. Now, part B is much more straightforward. Determine the work function. This is the formula. The book uses the formula sort of the other way around. It swaps that and that, so it has Ke max equals HF minus W. But I tend to use it this way. I just think it makes more sense this way because this is the energy that's coming in to the electron, and this is the two forms of energy that the electron therefore gets. So that's energy in, energy out. That's the total, and that's what it gets turned into. So this is the energy of the photon of light that hits the electron. Some of that energy goes into the work function to get it loose in the first place. And the rest of that energy goes into that. So those two add up to that. I just think that makes more, common sense. That represents more what happens. However, the one in the book is fine. It works. It's just a juggled version of this. Right. So you can use any trial that gave you a work function, that gave you some stopping voltage here. All right. So I've just picked trial 3, green light. HF. They gave us the frequency of the light in the table. Right? Work function is what we're trying to find. Maximum kinetic energy, excuse me, is equal to the stopping voltage, but you've got to multiply it by 1.6 by 10 to the minus 19 to get it in the right units. Right? Juggle that around, find W. W equals 2.1 electron volts. Question 18. Now there's a table on a page in your Ed Rollo book. I think it's on page 403. It's 400 and something. It's 40 something. I think it's page 403. That literally organizes these equations about de Broglie wavelengths and momentum of photons and all that sort of stuff beautifully well. Right? That table should be in your cheat sheet. Right? It's not done particularly well at all on the physics data sheet that they give you with your exam. So I would absolutely go to that. I think it's page 403. It's very close to that. It's 40 something. And I would find that table and copy it verbatim into your cheat sheet, right? Because this is very easy to forget, and it's very easy to get it the wrong way around. It's very easy to use a formula that's meant for photons on electron momentum or something like that, and you end up getting lost very easily in these questions. Okay, so this question is about an electron that's accelerated from rest to a particular speed by an electric field with a potential difference of 10,000 volts. Okay, determine the de Broglie wavelength. Excuse me. Okay, formula for de Broglie wavelength is this, right? Planck's constant divided by its momentum. And this is the momentum of an electron, so it's either mv if we get the v, but we didn't, so you have to find another way to do it, right? This is the other way to do it. That's the link between momentum and kinetic energy, right? That is from rho equals mv, the momentum formula, and k equals a half mv squared, right? If you, excuse me, if you combine those two and juggle it around, you end up getting this. Okay, so the electric field strength, excuse me, which, electric field strength, what am I talking about? The energy, right, is QV, which is 1.6 by 10 to the minus 15 joules. So that's how much energy it had, right? That goes in there, multiplied by 2 times the mass of the electron, right? Look that up, it's on the data sheet, 9.11 by 10 to the minus 31, I think it is. Square root it, get that answer, right? That's the momentum. And then finally you can do this, 6.63 by 10 to the minus 34 divided by that number, and comes to this. Right? And it's a wavelength, so it's in meters. Right? Again, what's the units? You don't want to do all that, get it all right, and forget the unit. Part B, it says calculate the momentum of a photon that has the same wavelength as the de Broglie wavelength in the electron. Okay, well, if it's got the same wavelength, the wavelength is that, 1.23 by 10 to the minus 11. This is the formula for the momentum of photons. Right, it's h divided by the wavelength. Really easy. Get the answer. Okay. Okay, question 19. This is another one of those nightmare questions, and you've just done 100 marks worth of physics exam. You're 2 hours in. You've got half an hour left, and you see this, and it says the visible section of the emission spectrum for hydrogen is shown here. Explain how the emission spectrum for hydrogen provides evidence that an electron has wave-like properties. Oh my God, right? You just want to go to sleep and you're faced with this. So here's how to do it. It's worth 3 marks, so you don't have to write an essay on this. It's not worth 8 marks. It's not enormous. But these are the things that the answer must include. Right? And again, I've tried to get my answer a little bit different from the other answer that NEAP gave, so that you've got a couple of ways to look at it. All right. Okay, so you have to somehow link the spectrum. Right? So this is the starting point. You've got to start there and you've got to end there. It's the whole idea. You have to sort of join the dots. You've got to start and show the way to get from the emission spectrum to the wave-like properties. That's what you're doing. In most of these explain things or relate, etc. Okay, so start at the spectrum. The spectrum is showing that only a few specific energies exist between the upper and lower electron levels, right? All of these things are happening. This light is being produced when electrons jump up to another electron level that they're not normally orbiting in, and then jump back down and release that extra energy in the form of light. The fact that they only release a few specific amounts of light all the time, same ones every time, tells you, excuse me, that there are only a few particular jumps possible, and they are always between the same locations. So anytime you do this to hydrogen, someone's going to do this 10 years from now in hydrogen, they're going to get that, because those electrons are still in the same place, and they can only jump up to the same place they've always jumped up to. All right, so that's the first point. So therefore, the levels themselves must be specific. The places where electrons are able to orbit must be very specific and very rare. There are only a few possible jumps between them, right? Only a few exist, and it's always the same few, right? Every time you do this, you don't just get 4, you get the same 4. Okay, so waves resonate as standing waves, right? Electrons are in orbitals that enable standing waves to happen, right? Therefore, they must have wave-like properties, right? If they didn't have wave-like properties, then the fact that they're making standing waves, or the fact that they have to fit into something that resonates, wouldn't be relevant. It wouldn't be it wouldn't be a requirement of their existence. But this, excuse me, but this evidence, the fact that they're always in exactly the same place, and it happens to be, once de Broglie came up with the whole idea of the Broglie wavelength for things that have matter, and Niels Bohr did the maths and figured out that these particular levels of energy correspond to the right de Broglie wavelengths to resonate their way around a nucleus. Right? That was absolute proof that electrons have wave properties. So this is the short way to say all of that stuff that just came out of my mouth. Okay, so that's the answer to question 19. 20, last one. Okay. Bunch of scientists determining the wavelength of their class laser. Right, they set up the apparatus shown to irradiate a hair of known width d and measure the distance between the central maximum and the first bright spot. Right. L represents the difference between the plane of the hair and the screen. All right. The students become aware that the pattern observed on the screen would be identical to a pattern created when a laser is fired at two very small slits that are a distance apart equal to the width of the hair. I'm just going to stop and show you why that works. Okay. Barrier. Here's a barrier with two slits in it. We've seen this 100 times before. Light shines towards it. In fact, I should probably have drawn it as a bunch of wave fronts like this. And they will diffract, okay? And the two of them will interfere with each other. Same thing happens with light going around something. It's like a hair. So here's a big fat hair. That acts like the middle of the barrier. So waves that come at this thing are still going to divert that way. Right? So they're still going to bend this way. They're not going to bend over here. They're not going to do the outside of the curve. That's not going to happen. But the inside part will still happen. Right? Because after all, that is half of this. If I just sort of draw another wall here, now we've just got two holes again, just like this. Right? But if they're not there, the only thing that's missing is the outside of the curvy bits, the outside of the curved diffracted path. They will still diffract inside to each other. So all of this will still happen, and you'll still get the interference pattern, which causes the bright and dark spots, or the constructive and destructive interference. Right? So that's why what they just said works. Now let's get back to the question. Okay, back to the question. Right. The experiments are repeated with a number of hairs of different widths. Gee, I wonder if that's the independent variable. The width of each hair is determined using a microscope measurement system. Okay, the length is 5.5 meters for each hair used. Okay, yeah. Explain using physics principles the effect of increasing the width of the hair on the pattern produced on the screen. That's the physics principle. That's the formula. Okay. Now, the width of the hair is analogous to D, right? The gap between, the distance between two gaps. So the wider the hair, the wider the distance is between the gaps that the light can go around the hair. All right. So the effect of increasing the width of the hair, if that goes up, if that number goes up, that number is going to go down because it's on the bottom of a fraction. Okay, they're inversely proportional to each other, so that doubles, that halves. Right? And that's pretty much all you have to say. You have to establish it using this. This is the physics principle. Right? And you have to say if the D increases, the delta X decreases, because that's algebra, baby. That's pretty much it. Right. Part B, identify the independent and dependent variables in this experiment. They were changing the width of the hair. That's the independent variable. They were measuring delta X. I know the experiment said they are trying to determine the wavelength of their class laser, but they're going to calculate that. They're not measuring it. Right? A dependent variable specifically is measured. It's what you get, the raw data that you collect while you're doing the experiment. Right? What you calculate later on is your own business, but they're not variables. Right? They're calculated bits and pieces. Right? The variables are things that happen during the experiment. So they were changing the width of the hair. They were measuring delta X. All right. Next. Excuse me. Part C. This is pretty easy. You just have to, they just ask you to fill out this page. It's 1 over D. It's meters to the -1, and that's meters. So they're not trying to fool you with units. So you just have to get the inverse of all of these numbers and write them down. Okay. To the right number of significant figures, which is 2. These are 2 significant figs. Put them in 2 sig figs over there, and you've got the marks. That's pretty easy. All right. 2 marks. All right. D. Now, I've just said C criteria here. We've done this enough to know how to draw a graph. Right? Plot a graph of delta x versus 1 on D. Right? And they've even said delta x on the y-axis, 1 on D on the x-axis, in the grid provided below. Include an appropriate scale for the y-axis and the x-axis. Draw a straight line of best fit through the plotted points as best you can, right? Include uncertainty bars for the x-axis only. Now, uncertainty bars, they gave you the uncertainty of it here. They said plus or minus 0.1 by 10 to the 4. So do that. Now, this, for the first time, I'm actually going to show you what the answer was and the criteria were from NEAP, because they did a very good job of this. So here's the answer. There you go. Okay, if you can't quite see this on the screen because it's a little bit small and I haven't zoomed in, right, get your own copy, because I've given this to you weeks ago, and have a look at what matters. Okay, it's a mark for a correct axis scale on the y, another one from the x, a mark for correctly plotted points, obviously, one mark for plotted points occupying at least half the vertical and half the horizontal grid, right? In other words, as I've been telling you for 2 years, the graph needs to be big. It needs to fill most of the space. So from there to there has to be at least half of the up and at least half of the across. If it isn't, you don't get that mark. Right. One mark for putting the uncertainty bars in. They're all plus 0.1 and minus 0.1 according to the scale that you put in. And a mark for a line of best fit that goes pretty much through all the points, or is at least in a reasonable position. All right. And we have made it to the last 3 marks of this exam. Excuse me. Okay, use the straight line of best fit drawn in part D to find the value of the wavelength of laser light. All right. This is a jumbled around version of that, which means the gradient, is delta x divided by 1 over d, right? Rise over the run. Now, divided by 1 over d is the same as multiplied by d, you know that, right? And so delta xd, is the gradient. But according to this, the wavelength is delta xd divided by L. So you can get the gradient of the graph divided by 5.5, and that'll tell you the wavelength of the laser light. So that is what answers the question that they were trying to answer by doing this experiment. And all you had to do was use that line of best fit to figure that out. Now, use the line of best fit to find the gradient, pick 2 points that are on the line, grab the gradient, divide it by 5.5, and you're going to get that answer. And that is the end of the exam, my friends. Thank you very much for listening.